Hi everyone, welcome to Jerematics Tutoring. In this video, I'll be showing you how to simplify radicals. So before I show you how to simplify radicals, I want to talk to you about a bit about what a radical is, and a bit of the vocabulary. So a radical is this symbol right here. As you can see, it looks like a little checkmark symbol. And you've got something inside called an index. And this index goes inside of your hook. So, for example, if you got an index of 2, then you're taking the square root of something. This means, this is like the opposite of raising something to an exponent. So for example, if you're squaring something, you're multiplying a number by itself. But if you're square rooting, you're trying to find a number that multiplies to itself to get what's inside of your radicand. A radicand is what's underneath the square root symbol. It's what's inside of the root. It's what's inside of your radical, basically. It's called a radicand. And the end right here is called an index. And if you don't see anything inside of the hook, then it's assumed to be 2, because you're square rooting. And this entire thing is called a radical equation. There are 2 different kinds of radicals. There is a mixed radical and an entire radical. The difference between a mixed and entire radical is pretty easy. It's pretty simple. It's a mixed radical is something like this, 2 square root 2, and an entire radical is something like this. Well, what's the difference? This is how I remember it. The difference between a mixed and an entire radical is an entire radical, your entire number is underneath the radical. And in a mixed radical, well, you've got a number in front and inside. So the way you can look at this is, well, entire radical, the entire thing is underneath the radical, and in a mixed radical, well, you've got numbers mixed in together. You got one in front and one inside. So if you have one in front, a number in front, and a number inside, it's mixed. And if all you have is numbers inside of the radical, then it's entire, because the entire thing is underneath the radical. That's how I remember it, and it's pretty easy to remember it that way. Well, how do you simplify radicals, first of all? Well, what you do is you break down the number inside of the radicand and write it as a big group of factors. So you find all of its factors, basically. You find all of the numbers, all of the prime numbers that multiply to each other to obtain your number inside the radicand. This might sound a bit confusing to you right now, but I will show you, and it's not as hard as it sounds. The first example I'll be giving you is square root. And you know what? Normally you don't write a 2 inside, but I will write a 2 inside, just so you know we're square rooting. But normally, if you're square rooting something, you never have to write a 2 inside, or you will never see a 2 inside. Let's say we're taking the square root of 16. And as you already know, the square root of 16 is 4, because 4 times 4 is 16. But I'm going to show you step by step on how to do this. So the square root of, how do you write 16 as a large set of products? Well, it's 2 times 2. Well, it's 4 times 4. It's 4 times 4. And after that, we can break it down into 2 times 2 times 2 times 2, like I was about to do. But first, I'll start with 4 times 4. 4 times 4. 4 times 4. And then after that, we can write 4 times 4 as 2 times 3 times 2 times 2. 2, 2, 2, 2. Of course, I could have just simplified it right from here, because this is a perfect square, right? So a radical will be gone completely, right? 4 times 4. And when you're simplifying a radical, what you do is you look for pretty much factors that appear this many times inside your radical. So you look for factors that appear n number of times inside your radical. So for example, if your index is 3, cube root, then you're going to look for factors that appear 3 times. And then if you're square rooting, you're looking for factors that occur twice. And what you do with these factors, you underline them. If there's 2, see 2 and then 2, and you separate into groups of n. So since the index is 2, you separate into groups of 2, if the factors are the same. So if there's 2 4s, there's 4 2s, and then we can separate them to 2 groups of 2s, right? And since they're all underlined, this means it's a perfect square. And what this means is you literally pull out one of these, one of the things that you underline. So if you got 2 4s, it's just 1 4, because you're square rooting 16, right? And if you square root something that's multiplied by itself, well, it cancels out the radical, right? Allow me to demonstrate. You've got square root of 4 squared because 4 times 4 is 4 squared, and then the radical eliminates your squared, and your squared eliminates the radical, and you're left with 4. And then your radical's gone, right? Or even in this example, it's 2 to the power of 4. The square root of 2 to the power of 4. Well, what's the square root of something to the 4th power? Well, you'll simply get the number squared. So you get 2 squared as a result, and then you get 4. So you see, come back to the same thing. Now I want to give you an example where you cannot remove the entire thing. Let's say you've got 8. 8. The square root of 8. How do you write out 8 as a product of its prime numbers? Well, you do this by writing 8 as 2 cubed, 2 times 2 times 2. And we're looking for factors that appear 2 times. And it appears 3 times. So what we do is, since it appears 3 times, and we're only looking for things that appear 2 times, we just underline 2 of them. We underline 2 of them, and then after that we take the square root of this, and remember, the square root of something multiplied by itself is simply the number itself, which is 2, because 2 squared, the square root of 2 squared is 2. So we got a group of 2, then you just take 1. And if you underline a group of 3, then you just take out one of them. It's always like you highlight your whole group, but you're only pulling one of them outside of the radical. And then we pull this 2 outside of the radical, and then this gives us 2 root 2. To repeat once again, you highlight your group of 2, because the index is 2, and then you just pull one of them outside of the radical, and then these 2 are gone, and then you're just left with this 2 right here inside of the radical. That's how I do it. And it's pretty easy to do it like that. The next example I'll be giving you will be to convert a mixed radical back to an entire radical. So for example, we've got, let's say we got 5. 5 square root of 3. How do we simplify this? Well, think about it. Since when you're converting an entire to a mixed, remember when you have a group of something and you highlight both of the factors that are the same, you just pull out one, right? What do you think is the opposite of taking the square root of something? You're squaring it. So if you're going to actually pull this inside of the radical, you square the number. You multiply by itself. So we pull the 5 inside, and we multiply 5 by itself. And then if we multiply all this stuff together, we get the square root of 125 times 3. What's 125 times 3? That's 375. So we're left with the square root of 375. And then if we want to convert this back to a mixed radical, then what we do is we break it down. We break it back down into its prime factors. So we get square root of 5 times 5 times 3. And since the index is 2, we look for a group that appears twice. And we got 2 5s. And then we pull one of the 5s out, and then we take out, and then we cross out these 2 5s inside of our radical. And then we just simply place the 5 in front of the radical. And we get left with 5 square root of 3. In this part of the video, we'll be looking at some advanced examples of converting entire radicals to mixed radicals. In this example, it's a cube root involved, and we got a very large number, as you can see, 1080. And like I said earlier in the video, when you're trying to simplify these radicals and convert an entire radical to a mixed radical, what we're trying to do over here is we need to break down this number to all of its factors and write it as a product of all of its prime numbers. And a prime number are numbers like 2, 3, 5. It's basically numbers where the only factors of that number is like itself in 1. So like 2, for example, 2, you can't really break it down. Well, of course you could represent it like as a multiplication of decimals, but prime numbers are not decimals, they are simply integers. So it's like 2 times 1. The only way to get 2 is 2 times 1, 3 times 1, so on and so forth, right? 1080, how do we write that as a set of factors? Well, what we do is we use the tree, 1080, and when I like to work out these multiplication trees, I like to always divide the number by 2, and then keep on dividing itself by 2 until I can't divide it by 2 anymore. And then after that, I work with the 3s. That's how I like to do it. And you know what? It goes pretty fast that way. So for example, 1080 divided by 2 is 540. So we can write it as 540 times 2. See, we've already put our first 2 branches. Then after that, 540 divided by 2. 270 times 2, right? Times 2. And then we carry down this 2. And then 270 divided by 2. That's 135. So 135 times 2. Times 2. Times 2. Bring down these little branches. 135. Can we divide that by 2? No, we could, but that would give us 60. That would give us 67.5, and we're not looking for decimal numbers over here. We're looking for numbers that are integers and are not decimals. 135. What if we divide that by 3? If we divide that by 3, what do we get? We get 45. So we can write this as 45 times 3. So 45 times 3 times 2 times 2. And we can even verify our factors from time to time to make sure it still multiplies up to what's on the top. So for example, 270 times 2, 540, times 2, 1080. 135 times 2, 270, times 2, 540, times 2, 1080. 45 times 3, 135 times 2, 270, times 2, 540, and then times 2 again, 1080. 45, can we divide this by 3? Yes, we sure can. This gives us 15 times 3. We bring down all the branches to connect them. 15 times 3 times 3 times 2 times 2 times 2. Oh, what's 15 divided by 3 is 3 times 5. So at the end of all of this, we get 5 times 3 times 3 times 3 times 2 times 2 times 2. And then to verify it, 5 times 3, 15, times 3, 45, times 3, 135, times 2, 270, times 2, 540, times 2080. So this is how we'd write it as a product of all of its prime factors, including repeats. So this is equal to the cube root of all of these numbers being multiplied by each other. So 5 times 3 times 3 times 3 times 2 times 2 times 2. 5 times 3 times 3 times 3 times 2 times 2 times 2. And what's the index of this radical? The index is 3. So we are looking for factors over here that appear 3 times so we can pull them outside of the cube root. We've got 3 3's, so we can highlight our 3 3's, and we highlight our 3 2's. And remember what I said earlier, is if you highlight a group of 3 and your index is 3, you cross out your entire group and you only pull one of them outside of the radical. Here's one thing that's very important to note. Well, you've got a group of 3's and a group of 2's. What do you do with this? Well, what you do with this is you simply multiply the number of your group by the number of the other group. And do not multiply all of your 3's and 2's together. You just multiply 1 3 by 1 2. Because whenever you pull outside of the radical, only one comes out of it because you're cube rooting a cube. And if you cube root a cube, well, it cancels each other out and you only get 1, right? It's like a cube root of 3 cubed. Well, 3 times 3 times 3. And then you cube rooting, well, you're like, well, we're trying to find a number that multiplies by itself n number of times to get the number you started with. And it's a cube, so you undo the cube and then you get 1, right? So it's 3 times 2. Because cube root of 3 cubed is 3. So 3 times 2. Because 2 cubed, the cube root of 2 cubed is 2. So 3 times 2. So this gives us 6. And what we do with the 6 is we put it in front of the radical. So we get 6 cube root 5. So we get 6 cube root 5. And that's how you do that. Well, what if you want to verify your answer to make sure that it's right? Well, remember, like I said, is when you pull a number outside of the radical, you're looking for a number that multiplies by itself n number of times, as indicated in the index, and then you eliminate it and just take one of it outside, right? If you're going to pull a number inside of the radical, you do the opposite. You multiply the number outside of the radical by itself n number of times and multiply by what's inside of the radicand. And what I mean by that is 6 cube root 5 would be written as the cube root of 6 cubed, because when you pull this inside, the index is 3, so you multiply 6 by itself 3 times. So 6 times 6 times 6 times 5. What's all of this multiplied by each other? Well, we should get 1080, but let's just make sure. So the cube root of 6 times 6, 36. So 36 times 6 times 5. This is 180, 216. So this gives us the cube root of 216 multiplied by 5. And as you know, 216 multiplied by 5 is 1080. So we get the cube root of 1080. And this is indeed the right answer. So that's how you simplify advanced radicals when you got a cube root involved and you've got a very large number that you need to break down. So if you follow these steps, you're bound to succeed. So thank you for watching this video, and I hope it helped you. And if you have any questions, feel free to leave them down in the comments below. I will answer them. Thank you, and have a great day.